Hello everyone, welcome back to my tutorial. In this tutorial, we are going to solve a pressure vessel with the shell element. So I have the pressure vessel of 2 meter diameter and 3 meter length. It has a thickness of 0.01 meter. The thickness is very less. By modeling this much small thickness using a solid element, so that will give more stress, and that is because of solid element stiffness. For that, we have to model it as a shell element to capture displacement and strain, everything in proper way. So this is my pressure vessel, simple model I have taken, and it has the material of steel with an Young's modulus 210 gigapascal and Poisson ratio is 0.3, and the boundary condition is the both edges, this edge and this edge, I'm just arresting the fixing it, and internal pressure I'm applying in 1 e power 5 Pascal. So this is our case, and I have calculated simply with an hand calculation. Hoop stress is coming around 10 megapascal and longitudinal stress is coming 5 megapascal. Now we'll do finite element analysis using salome, then we'll check how much we are getting it in FEA. So I just opened salome. First we'll model geometry by using a geometry model. So to create this geometry, so I'm going to use simple cylinder. First options, X origin is this one, vector is Z, radius it is asking, but here I have specified diameter, the radius is 1 and height is 3. Go to fit screen. So this one is the cylinder, just apply and close. Now I have created the cylinder. I don't want inside solid, only the outside surface only I wanted. Just go to here, there is option called explode. Here surface, face, select the surface. We can select the surface, from that we can explode. Outer surface, just apply. Here you see we got only the outer surface. Now we have done creating the geometry. Now we have to create the groups to apply the boundary condition. As in our geometry, these two edges we have to fix it, and inside surface we have to apply the pressure. So just select this face one. First we will save this geometry. Just go to file, save as, pictures, code aster. So I'm just saving it here. Go here, create group, edge group, this edge and this edge. Just add, you have to fix it. Just apply, go to surface, choose the surface, add. Here we have to apply the pressure. Just apply and close. Now we have created the groups. Then we can go for meshing model to create the mesh. Select this face one, mesh, create mesh. Go to NetGen 1D 2D. Instead we can go for quadrangle mapping also. I'm just choosing mapping. Here quadrangle parameter, choose the standard, just say OK. In 1D wire discretization, local length, this is I'm just giving 0.03, just say OK, apply and close. Right click this mesh one, just compute it. Now see, we have created a very good fine mesh, but only thing is the outside surface is the positive side and inside surfaces is negative side. But we have to apply a load in inside surface. For that we have to change the direction of this element. For that just go to modification, orientation, apply all, just apply. See, the direction is changed. So this one is the positive side. Whatever the load we are applying, it will apply to the positive side. Now just close. Now we have changed the direction. We'll save this file. We'll check the groups. Now both the groups are available. this yellow color is the positive side and green color is the negative side. So only whatever the force we are applying, pressure we are applying, it will apply to the positive side. Now, because we have to apply internal pressure, now we'll go for aster study, create the setup. So just go to aster study, just say OK. This is a simple linear static analysis. So we can create the setup one by one also. Just right click, add a stage, mesh. First we have to read the mesh. So mesh 1, MID format, just apply and OK. Then just go to model definition, assign a finite element. Go to here, edit, everywhere. This is mechanic. Actually this is not a 3D, this is cell. There are different shell options are available. So DKT, DKTG, DST we can use. There is one more option called CoQ3D also we can use. I have used here linear element. Here we cannot use CoQ3D because biquadratic element only applicable for CoQ3D. So I am just using a DKT element. Just say OK. Just apply and OK. Now just go to we have defined the shell element. We have to define the element property. Just go to model. Afikara element is the element property definition. CoQ, edit. So group of element is the pressure, is the group of element. Thickness we have to specify. APRs is nothing but thickness. So thickness of model is 0.01. Just say OK. Just apply and OK. Now I have defined the element property also. Now we can define the material. Just go to material, define a material, linear isotropic material. Young's modulus is 210 e power 9, Poisson ratio is 0.3. Just say OK. Just apply and OK. So material I have defined. Now we'll assign the material to the model. Go to assign a material, mesh and model, just everywhere, same material, just OK, just apply and OK. Now I have assigned the material. Now just go to boundary conditions, assign a mechanical load. Here we have to arrest the degree of freedom, enforce degree of freedom, edit. So here we have a group of element, edge element. Fix is the element, just say OK. And here we have to fix all the degree of freedom. So solid element we need not to apply rotational degree of freedom because solid element doesn't have rotational degree of freedom. But for a beam and shell element it has 6 degree of freedom, 3 translation and 3 rotation. So for that we have to arrest all the degree of freedom. So make it 0. We have chosen here fix. Just say OK. Just apply. And we just want to apply a pressure also. Here itself we can choose. Just press. By typing press, the command will come up. Because it has a more number of commands. So here there is an option called press rep. Just edit. So we have to choose the element, group of element. Pressure is the group of element. And the pressure value is, just go here. The pressure value is 1 e power 5. 1 e power 5. Just say OK. Just apply. Say OK. So now we have defined fixing load and pressure load in single command itself. Now we can save this file. After defining all, we can go for solver defining. Just define the analysis type. This is a static mechanical analysis. So material and element property we have to switch on. Here loads, we have only one load, that is a load. Just say OK. Remaining thing we need not to specify, it will set default, just apply and OK. So meca static is the solver to solve the static analysis. Now we have defined the solver. Now we just go for a post processing, call champ. So I'm just choosing a sigma element and node to view the directional stress as well as one meca stress. So this will calculate the equivalent stress, one meca stresses. Now just say apply. Here there is an option called unnamed. We just want to use the same name whatever the solver name used. So reuse the input object, just apply and OK. Then we just want to save the output. Just go to output, set output results, navigate the file into the folder. So I'm just naming it as result.rmad. Just OK. Choose call champ. This is not required anyway. Just tut-70 make it as. Just OK. Just apply and OK. So here actually this will not calculate nodal value, only the element value only it will calculate. So only element value only it will calculate, just apply and OK. So now we can solve this case. So just +1, 5 seconds, just run this case. If any error comes, it will show it here. From that we have to modify accordingly. Now it started reading the command file. This is a shell element. It is solved without any error. So now we can view the results by using a paraview. Just go to paraview. Just open. Shell element. So this is the result file. Just OK. Now we have calculate SIEQ and SIGM LNO and displacement. So just apply it. Here you can see only the displacement. So this is the displacement value. If you want to see here you cannot see this equivalent LNO and sigma LNO. To get this value, just go to filter. There is an option called mechanics. Here you just choose LNO field to surface. Just apply. Now just go here. You can see it now. Sigma LNO and sigma equivalent LNO. Now just sigma LNO, sigma. This is X value. This one is the Y value. Similarly, just go to one meca. Now we'll check with the displacement. So how it is behaving. So this one is the X displacement. It is bulging in this way. This one is the Y. Similarly, this one is the Z. Now just go to equivalent. Here we have to read the data actually. Here we are not calculated properly. Paraview is not visualizing the data. Further, just go to aster study. Here there is an option called after doing a call champ, we have to do with the post champ. So use the any name we can do. I'm just extract the mid surface shell element. It has a mid surface, inner surface and outer surface. I just want to extract the mid surface data. I'm just naming as mid, extract coq, edit. So norm champ is SAEQ no. SAGM no. SAEQ ka both we have to calculate actually. SAGM ka similarly for SAEQ ka. Yes, this 4 thing has to be calculated, and this one is make it 1. Now we kochi and new kochi. You just this is the inner surface, mid surface, outer surface. I just want to take it as mid surface. Just say OK. Here there is option called from the meca static also we can calculate or wrestling. So I'm just choosing this wrestling. Just apply and save OK. Now this mid I'm calculating. I just want to save this mid. Just go to output, set output results. So I'm just naming it as mid surf dot rmed. Just save. Here mesh. Here instead of wrestling we have to choose mid post champ. So here tau champ make it yes. So just OK. MAD format. Just apply and OK. Now we can open this mid surface to view the results. Now we can save this file. Go to history view. Delete the previous run and run the case again. Now it is started solving. Now it is solved. Now we'll go for a post processing to view the results. Just go to paraview. Just right click and open. Here there is an option called midsurf.rmd. Just select this file. Just OK. Now we got this both of data. Just apply it. Now here we just go. There is no data here. Just go to filter, mechanics. So there is an option called Elga to surface. Just apply. No, instead of Elga to surface, Elno to surface we have to choose. Filter, mechanics, Elno to surface. Just apply. Here you can get same mid SAEQ no and mid SAGM no. So yes. This is actually a magnitude. We have to see the von Mises. So now we are getting a von Mises stress of 9.3 megapascal. From the hand calculation we have got OOP stress of 10 megapascal. It is very closer to that data. So here we are fixing it. That's why here the stress is very less. Other data, so outside the boundary condition we have to check the data. Okay, now we can check the sigma also. So this one is the sigma L no. So here sigma xx we are getting 10 megapascal. So exactly we are getting sigma xx. So x is this direction. So this one is the hoop stress direction. And y we are getting, y is also the same direction, but we are getting This one is the Y data, and Z is we are getting 0. So in this tutorial we have learned a shell element using a DKT element to calculate the pressure vessel. Next tutorial we will see how to use CoQ3D element to solve the same pressure vessel. So thank you for watching my videos. Please subscribe my channel for more videos. Thank you.